Okay, so hi everyone. Now we are going to look at the time series component, which is basically we are going to start with the Engle Granger approach. So I'm actually working on the assumption that you have read the sheet, which was also posted together with these slides, where basically you have to acquaint yourself with a number of concepts that are commonly used in the time series analysis. Just to sort of continue, we are actually going to look at the so-called error correction models. So now, what are error correction models? These are usually category of multiple time series models that directly estimate the speed at which the dependent variable or the regressant y returns to equilibrium after a change in an independent variable x. So in other words, the error correction terms gives us or tells us how fast or how slow does y returns to its equilibrium after changes has happened in the x variable. All right. So, and that's why it's for that reason that the error correction models are very useful in estimating both short-term and long-term effects. The basic structure of the error correction model is given such that change in y is equal to alpha plus beta change in xt minus 1. You can actually note here that this is the past value of x, this is the current value of y, obviously minus beta ec, which is the error correction term, which tells us the speed of adjustment, which is also lagged by 1 period. And you can also actually see that this should be a negative, should carry a negative sign. All right. So, and that's why we can actually then sort of summarize and say this error correction model basically shows us the short-term effects of x on y, long-term effects of x on y, which is basically the long-run multiplier, and then the speed at which y returns to equilibrium after a deviation has occurred. And maybe just to add to that, we can also actually add that it actually deals with both integrated and stationary time series data, and also it can also be estimated using OLS, ordinary least square, and you can actually use these type of models to actually test different economic theory, whether it's micro or macro. And as we indicated earlier, we said the error correction is actually appropriate when we have time series data, and we are also interested in short-term and long-term relationship between a number of variables. Okay, now we remember that we said stationarity has got to do with mean constant being mean variance and covariance being constant over time. So, and that is for that reason we are basically then saying stationary time series data are mean reverting. So in other words, they have a finite mean and variance that does not depend on time, and this is basically how we express it. Now, if this coefficient is less than 1, then we are also assuming that the error term is also stationary with a mean value of 0 and a constant variance. Okay, and now if this row is between 0 and 1, then we are basically saying the time series is stationary, but it contains autocorrelation. Okay, now when the time series is not is non-stationary and but appear to be integrated, then usually it's not mean reverting and it appear to be, on a random walk. And also we have been then basically saying there are some memories. In other words, the effect of any shock is permanently incorporated into the series, and usually it has an infinite variance and there's no mean. Okay, so you can see actually that all these characteristics are the opposite of the stationary time series variable. All right. Now, and that's why we can basically present that, in a formal way, the integrated series can be expressed as a function of all past disturbances at any point in time. We basically just sum to say you can either express it in the following manner, where you have y as a function of that, whereby this rho is equal to 1, or we can express it as follow, where we have a difference of yt minus 1 is equal to mu t. In other words, we are basically saying that this is your current value of t, this is the past value of t, so the difference between them, you have the then give is equal to mu t now, but we are saying this mu t is equal to et. Remember that we are saying et is stationary, okay? And so therefore, if it's stationary, then we are saying that the expected value of the error term must be equal to 0. So that's why we're saying mean 0 and the constant variance. So if that is the case, then it actually then implies that that error term is stationary, and so is the mu, okay? Because this mu is an estimated one, okay? It's an estimated one. Okay, so then we can go and also talk about order of integration. Now, what is the order of integration? So order of integration, so a variable or a series can be integrated of either order 0 or order 1 or order 2 or higher order. And that's why we say integrated time series data are stationary after being differenced. So what are we saying here? The variables that are integrated, so they might not necessarily be integrated of order 0, but they can be integrated of order 1 or up or whatever, however many times it's differenced. So then we can actually say, if we refer to the number of times being d times, then it means that the integrated of order is d. So if it's 1, then the order of integration is 1. If it's 2, then the order of integration will be 2. So but for our discussion, will only focus on the first difference between, which is basically the integration of order 1. So in other words, in most cases, once you difference the variable once, then it becomes stationary, okay? And it's basically a common strategy in time series. So theoretically, we can actually explain that the sources of integration can either be the past shocks that are permanently, um, permanently incorporated into the memory of the series, or basically the series is a function of other integrated processes, okay? All right, so let us just look at this graph very carefully, okay? So we are talking about a drunk's random walk, okay? Let us consider that it's an individual who's drunk, and this is his or her random walk. Okay, fine. Let's move further. Just keep that in mind. Usually, analyzing integrated time series in level form dramatically increases the likelihood of making type 2 error. What are we saying here? Remember that when we are estimating a basic OLS, a simple OLS, we usually don't treat the data. We don't really check whether the data are stationary or not. But so they are usually assumed to be integrated of order 0. Okay. Or sometimes they can be integrated of order 0, but then if that is the case, then you are likely to commit type 2 error. And what does that mean? That basically means that you are likely to have also a problem of spurious association, whereby the variables will show to have a relationship, even such a relationship does not exist. Even such variables do not relate in any way. And in most cases, you'll have a high R square and a small standard error, but at the same time, the t values are so inflated, which doesn't make any sense. And usually, dealing with this problem then requires us to actually um, difference the variables so they can become stationary. So all these things will become much clearer as we do the practical video. Okay, so therefore when you difference the series, you actually solve the problem of spurious regression. In other words, there's nonsensical problem. But then another problem is created because sometimes when you difference the variables, you throw away some important information, okay? You throw away some important information, okay? And remember that most of this model also involves lagged difference variable, and where they are assumed to have an effect on the x, where we assume that the effect of x variables on y never last longer than one period. Okay, so in other words, if you are modeling a variable that has lagged variables or lagged difference variables, you are basically saying the effect of the independent variable on the dependent variable is short-lived, and that's why it becomes a short term. And that's why we are saying when you difference them to solve the problems of spurious regression, it creates another problem because you are throwing away important information. And why are we saying so? Because you are throwing away that important information, because what if these variables have a long-term relationship and you have differenced them because you want to get rid of the spurious regression problem? And so that's why we are basically then arguing that if the time series share an equilibrium relationship with an error correction mechanism, the stochastic trends of the time series will be correlated with one another. And that's actually what we are going to discuss next, which is basically the concept of co-integration. Okay, now what is co-integration? Co-integration, basically, we are looking at, so if we consider two time series that are co-integrated, we are basically saying if there is co-integration among the variables, they should have some long-run relationship. So, but to start with, we are basically saying if both variables are integrated of the same order. So if we assume that maybe they are all integrated of order one, and so then that would actually also mean that there should be a linear combination of the two time series such that they are stationary in levels. Okay, so some linear combination of these variables should have some stationarity, and so if there's such, then we can then say, okay, if two or more series are co-integrated, or we can basically say two or more series are co-integrated if each has a long run component, but these components cancels out between the series. Okay, in other words, they share a stochastic, or they share stochastic trends, and we are actually going to demonstrate that with a graph that we were talking about. Now, co-integrated data never expected to drift too far away from each other. In other words, co-integrated variables usually have a co-movement as time goes by. And this co-movement means that these variables tend to actually maintain some equilibrium relationship. Okay, now, and so that's why if we go back to that example of a drunk random walk, okay, now if that random walk, well, let us call it x. Okay, so if the random walk is expressed by xt minus 1 is equal to mu t, so mu t represents a stationary process or a white noise shock. Now let us say we have this random walk has a dog, which is expressed by yt. Yt minus 1 is equal to wt. So where wt represents a stationary white noise process of a dog step. So the dog steps depend, let us say now, these dog steps depend, they have the dog steps, we also have the drunk steps. So let us just go to that graph. So this is the dog steps. So now when we can say if these two are, so now we are saying, what if this dog belongs to that drunk? Okay, what is likely to happen? We can actually assume that there is likely to be an equilibrium relationship, and these variables are likely to be co-integrated. Why? Because the deviation, there is likely going to be a deviation, but this deviation will be corrected over time. And if we go and look at this drunk and her dog, usually, yes, there will be some deviation because her dog will not necessarily just continuously, walk the same steps as the drunk, the owner. But as time goes by, you can actually see that the deviation will be corrected and there will be some equilibrium in the long term. And that is basically what we talk of in terms of co-integration of variables that are integrated of the same order. Okay, that will then constitute the end of the first part of the lecture.